So our next talk will be given by Isabel Quant from the University of Bristol. Surface tension measurements on microsecond timescales from single picometer droplets and collisions of H droplets. Thanks, Isabel.
Hello everyone, so I'm Isabel in the business group at the University of Bristol.
Right, go.
Okay, so aerosols can have a climate cooling effect by acting as cloud seeds or cloud condensation nuclei. They become CCN when they surpass the critical saturation barrier defined by the polar equation. And this barrier can be lowered with lower surface tensions. The surfactants can lower the surface tension of aerosols, which can have implications in terms of the CCN formation predictions that models make, as well as accelerated chemistry that takes place at the droplet air interface. Atmospheric. So surfactants are in the atmosphere, mostly coming from natural sources such as sea spray, shown in the figure. But they also have anthropogenic sources like fuel consumption and cooking oils. They have been found in relevant concentrations in the atmosphere to lower the surface tension of atmospheric aerosols. And because of this, it's important to study how they affect aerosol physical properties and what comes from that. So one way to study the surface tension of aerosols is by using a microdroplet dispenser. So the way that works is that the microdroplet dispenser dispenses a stream of droplets. And if you take a picture of the droplet at increasing time points, you basically get a moving picture of an oscillating droplet. And then by using LabVIEW software, I can put a box over that droplet, and then the ratio of the height and width of that box gives me the aspect ratio over time. And with aspect ratio over time, I can take the rolling average of that, form a fast Fourier transform at different stages of that oscillation, and get the surface tension at different points of that oscillation, using the equation below. And using the the aspect ratio can also accurately measure the droplet radius, which is important for calculating the surface tension. The limitation with using just one microdroplet dispenser is that the oscillations dampen at around 400 microseconds. And once your oscillations dampen, that's where your measurements end. And that's not enough time to investigate the surface partitioning of surfactants in solution. So the goal of my project is to re-excite droplet oscillation by coalescing two droplets that are older and therefore studying droplets with older droplet surface gauges. So the way I approached that was by building this setup. To briefly explain it, to the left and right of the setup, there are different translational stages that help me position the two different droplet dispensers and aim the two drops at each other. And then this middle translational stage and this vertical one here helps me move the entire setup up once I have everything set up. And the middle one helps me keep the droplet in focus, so because the camera is static. So everything has to be able to move relative to the camera. So when I built this setup, there was a lot of issues at first that I had to fine tune. And the main issue always comes down to the droplet stability of the coalesced droplet. So a few things that I had to optimize were the collision angle, the collision time, the sensitivity of the whole setup to the lab environment, and the method I used to calculate aspect ratio. So you'll be seeing a lot of plots that look like this, and this is somewhat of the gold standard that I was trying to achieve with the coalesced droplet. So a nice dampening oscillation of the aspect ratio. And then for all my trial and error, I was using water droplets. So I would want to see surface tension values of around 71 to 73 millinewtons per meter. So this is kind of the gold standard I was trying to reach. So at first, I tried to use, is the video playing? Oh, well. So at first I tried different collision angles. That's okay. What you would have seen in the video is two droplets that wobble a lot. And essentially, what that means was when the droplets are too old after being dispensed, their position that I can see in the camera moves too much and then they don't coalesce consistently and reproducibly. So that was the issue I was running into with a 40-degree collision angle. Then I tried a 90-degree and 110, and 110 gave me the best results. So that is the angle that I will use for the rest of the experiments. Then I tried different collision times. And what I found is that the earlier collisions, the better. This is similar to what I said for the previous slide. If you have older droplets, by the time that I'm actually coalescing them, and by the time I can actually use the measurements from that coalescence, they're too unstable. So the earlier the collisions, the better. And then I played around with how I calculate aspect ratio. So the box method works really well when I use a single dispenser because the droplets oscillate with not a lot of tilt. But when you have two droplets and you're colliding them, depending on their position for the coalescence, they start to tilt a little. And the issue with the box method is that the box doesn't tilt with the droplets. So if you have a bit of a tilt, you're measuring the wrong aspect ratio, and then your full measurement is not useful. To counter that, I tried the ellipse method that places an ellipse over the droplet and measures the longest point, the shortest points, and gets the ratio from that. And the ellipse method does follow the tilt. So I played around with measuring water with these two methods, and what I found is that the box method works the best when it does work, which means that I have to use it with the coalescing droplets. I have to maneuver them so that they oscillate with as minimal tilt as possible. And it's also the best method to get an accurate measurement of the droplet radius. The ellipse method works fairly well, although it does give me a larger error. And it's not always accurate, but it does follow the droplet tilt, which is a good thing. But it doesn't dampen to an aspect ratio of 1, which is necessary to get the droplet radius. So even if I use the ellipse method, I have to still stick with the box method to get the droplets radius. So the conclusion from those experiments were that if I can do anything to minimize the tilt of the coalesced droplet, then I will use the box method, but if not, I will use the ellipse method as a backup. So to summarize what I mentioned, the best collision angle is around 110 degrees. The best collision time is early as possible, which is normally around 400 to 500 microseconds. I didn't get into detail with this, but the sensitivity to environment to counter any vibrations caused by movement in the lab, we floated the table, and I also had a shield made for the LED light, because the LED light has a really strong fan. So to minimize the wind generated from that, I put a box on it. And then for the aspect ratio, the best method to measure this is the box method, but if not, I use the ellipse as a backup. I'm going to guess that this video also doesn't work. Yeah. Well, that was a video of a nice collision. You can use your imagination. So basically, these are my initial results. Like, as I mentioned earlier, I tried water at first, and there is a lot more noise with respect to single droplet measurements. But to highlight the novelty of the setup that I'm using, you can see that originally droplets would, a single droplet would dampen at around, here in this case, 300 microseconds. And I was able to successfully re-excite those oscillations at an older droplet age. With the first solutions or chemicals that I was trying to measure this with, we were using only solutions that we don't expect dynamic surface tension changes at older droplets. So ideally what I should see is the same values here and here. There's a lot more noise, but somewhat there, which is a good sign. So then I moved on to another solution and I tried 10% ethanol. It's a good sign that I was able to get the values that I was expecting, but there is a lot of noise. That could just be because ethanol is particularly finicky with these droplet dispensers. So to again test if this was actually working or if it was just a coincidence, I used 2 molar levulinic acid, which worked really, really well, with a lot less noise and quite a bit and really good accuracy. So then I also tried, out of curiosity, 4 molar levulinic acid, and again, pretty good results, which is quite promising. So basically, the work I've been doing has been trying to optimize how I coalesce these droplets. And the key is to focus on the droplet stability of the coalesced droplet. And with that, I was able to re-excite surface oscillations to measure surface tension values of droplets at ages that were previously inaccessible. So what I'm going to work on next, well, still under the theme of droplet stability, before all of my translational stages were essentially fighting gravity because it was upside down. So to try to minimize the sensitivity of touch to this setup, I've flipped it over, and I'm going to be trying to see if this setup works at having more stable droplets for collisions. And then if that works, the first thing on the list will be surfactants, and the first one I'm starting with is OTG at different concentrations. So that's what's coming in future work. And with that, I wanted to thank my supervisor, Brian Bisnick, Jim Walker, and the rest of the partner group.
Thank you very much, Isabel. Have any questions for Isabel?
Thanks a lot, Isabel. That was really great. In the very first slide, I think you said the PFAS was on the sea surface. Is that acting as a surfactant?
That was more so an example of just how from the sea surface microlayer, surfactants are injected into the atmosphere. I'm not specifically.
I'm interested to know if there's like an increased surfactants from these chemicals in the sea surface, or if you have any kind of knowledge of the increase in surfactants in the environment.
Well, that is where the majority of the surfactants in the atmosphere come from. So there's chemicals on the sea surface microlayer, and then bubble bursting or sea spray is what lifts that into the atmosphere.
Thanks. Question here.
Hi, Adam Squire, University of Bath, lovely talk. What's the time scale relative to your experiment of sort of evaporation processes that would then shift the concentration? So if you're like 10% ethanol, I guess eventually it would stop being that if ethanol evaporates quickly water or something. So is that the kind of time scale you can start looking at, or is that way off?
Yeah, I think we act under the assumption that evaporation isn't really taking place at a relevant scale at that droplet size at that time.
Thank you.
Andrew Bailey, University of Leeds. Are your droplets like about 50 microns?
The coalesced ones, yeah. So they're individually around 25 to 30, and then coalesced 60 to 70.
And you're doing them, the collision is sort of in plane. So do you align them orthogonally to the plane?
Yeah. So the way I kind of can calculate if they're both in line with each other is based on how I focus them relative to the camera. So how focused they are kind of tells me.
Okay.
Any other questions? Anton?
And let's just talk about really interesting talk. You mentioned that when the droplets are older, they become more unstable. Is that something that's sort of well understood why that happens?
I think the reason it is because it's not individual droplets. You have to remember that it's a stream of droplets. So at some point they will lose their momentum, and the reproducibility of their position will just be shifting a little bit, which normally for a single droplet measurement would be fine, because you're taking pictures on it and the blur wouldn't really affect your measurement. With the coalesced droplets, since I need them to hit the same spot over and over again to then measure the consistently coalesced droplet, that's where their position gets a bit finicky.
Thanks very much. If we could thank Isabel